Welcome to the module on continuity and differentiability. We're going to start with definitions related to continuity. Naturally, we start with a definition of a continuous function. And we are going to start with the notion of a function being continuous at a particular value a. And this is the case if the limit of f of x, when x is approaching a, is obtained by plugging x equal a inside the function. If this is not the case, we'll say that the function f is discontinuous at a, or that a is a discontinuity of f. Now you see that in this definition it is implicit that the limit of f of x at a exists, and in particular, if it were not the case, then we would have a discontinuity. Right? So in a situation like the one depicted in this graph, you see that the function doesn't have a limit at a, and therefore it is not continuous at a, because the limit does not exist. And similarly, it is implicit that the value of f at a exists. So if it were not the case, again, if you have a function that is not defined at a, then certainly it cannot be continuous at a. So here a is also a discontinuity, because f of a does not exist. And the key condition in the case where both the limit and the value of the function exist is that these two things are equal. In this third graph, you see that the function has a limit at a, has a value at a, but the limit and the value of the function do not coincide, and therefore again we have a discontinuity. So these are essentially three different types of discontinuity, and the last two are called removable discontinuities. The reason is because in both cases the limit of the function at a exists, and therefore we could make the function continuous at a by just changing the value at one point, just at a. So the function g of x here, that is defined by f of x everywhere but at a, and by the value of the limit of f at a when x is equal to a, is going to be a function that is continuous at a. It coincides with f of x everywhere except at a, and it is continuous at a. So this function in some sense removes the discontinuity. So in other words, a removable discontinuity is one at which the limit of the function exists. On the other hand, when the limit of the function does not exist, we're going to say that the discontinuity is non-removable. Now we already have seen a number of continuous functions, we just didn't call them that way so far. For instance, we have seen that to obtain the limit of a polynomial function at a, you only need to plug x equal a inside that function. What that means is that every polynomial function is continuous at each number a on the real line. Similarly, we have seen that at every point in the domain of a rational function, we can obtain the limit of that function by plugging in the value inside the function. In other words, every rational function is continuous at each point of its domain. Of course, points that are not in the domain, then the value of the function is not defined and we have a discontinuity. Additionally, and unlike for polynomial and rational function where we are just stating facts that we've already seen, we will note that sine and cosine functions are also continuous at each point of the real line. Now if we have two functions f and g that are both continuous at the same value a, and k is a constant, then when I multiply a continuous function by this constant, I obtain a new continuous function. In other words, the function kf is going to be continuous at a. And similarly, the sum f plus g and the product f times g are also going to be continuous functions at a. The reason for that is simply the limit laws that we have seen in the model on limits. So to see how it works, let's take a look at the example of f plus g, and this is exactly the same kind of argument for the other two. So we want to check that to obtain the limit of f plus g at a, we only need to plug in x equal a. For the limit of a sum, we know that it is the sum of the limits as long as all the limits involved exist. The limit of f of x at a exists and is f of a because f is continuous at a. And similarly, the limit of g at a is g of a and of course exists because g is continuous at a. Therefore, the limit of the sum is the sum of the limits, and it is f of a plus g of a, which of course is just the value of the function f plus g at a. So that justifies that f plus g is continuous at a if f and g are. Now you see that if we have two continuous functions at a, we use the standard operations and we get again a continuous function at a. But in this theorem, the quotient of two functions is not mentioned. So what happens if we look at the limit of a quotient at a? If we refer back to the limit laws that we have seen when we were studying limits, the limit of a quotient is a quotient of the limits as long as all the limits involved exist and the limit at the bottom is not zero. The limit when x is approaching a of g of x is going to be g of a because g is continuous at a. Therefore, we get the condition that the limit is obtained by plugging in x equal a if the value at the bottom is not zero. So that gives us this additional continuous function. F over g is going to be continuous at a if g of a is not zero. Now, continuity here is really just preservation of limits, right? It says that if x is approaching a, then f of x is approaching f of a. In other words, if you have a is the limit of x, then you apply a continuous function, and this continuous function is going to preserve limits in the sense that the limit of the image is the image of the limit. If I take a continuous function at f of a, then g should preserve limits, and therefore g of f of x should approach g of f of a. In other words, I can compose two continuous functions and obtain a continuous function. The more general statement here is that if I have a function f that has a limit L at a, and g is continuous at this limit L, then the limit at a of g of f of x is the image under g of the limit of f, in other words, g of L. In the particular case where L is just f of a, right, the case where f is continuous at a, then we get that if f is continuous at a and g is continuous at f of a, then g of f is continuous at a. In other words, composition preserves continuity. A point of terminology. Sometimes you will see that we talk about a function being continuous on an interval. So there are various kinds of intervals. Let's start with an open interval. Continuous on an open interval simply means continuous at each point in this interval. Now we could have a function that we call continuous on an interval that is, for instance, closed on the left. That means that f is continuous on the open interval and also what we will call left continuous at a, in the sense that the limit of f of x when x is approaching a from the right is f of a. In other words, we have the condition of continuity that to get the limit we plug x equal a inside the function, except that we can only look at the limit that is defined from inside the interval, so in this case from the right. On the other hand, the function is continuous on interval that is closed on the right endpoint, if f is continuous at each point inside the interval, and the limit of f at b from the left is f of b. Again, that means we have the condition of continuity, that is, to get the limit, you plug x equal b inside the function and you get f of b. But we have that only for the one-sided limit that is defined on that interval. Of course, continuity on a closed interval on both sides is continuity on the open interval and this one-sided condition at each one of the endpoints. So let's look at an example. Let's say this is a graph of a function f, and we are looking first for the discontinuities of this function. Well, you see that at -3, -3 1 and 2, we have discontinuities. In each case, in particular, the limit of the function does not exist. At -3 the function is not even defined. If we ask on the other end for the intervals of continuity, then the function is continuous on -∞ to -3, open at -3, because you see that at -3 we don't have this limit from the left that coincides with the value of the function at -3. But on the other end, the function is continuous on the interval -3, -3, where we can include the endpoint -3, because the value of the function at -3 coincides with the one-sided limit of f from the right at -3. The function is also continuous on the open interval -3 and on the closed interval 1, 2, because on this interval the function is continuous at each point of the open interval 1, 2, and at 1 the value of the function coincides with the limit of the function at 1 from the right, and at 2 the value of the function coincides with the limit of the function at 2 from the left. And finally, the function is continuous on the open interval to infinity. Now, it's not hard to see what happens if the function is given by a graph like that. In the next video, we're going to see more examples, and in particular, we're going to see what we can do from when the function is defined by an algebraic expression.